So on for today's seminar. This is a kind of a long anticipated event. We've gone back and forth with trying to schedule Rei off and on over the last probably 3 or 4 years. We've floated this idea, and it just never quite happened for no particular reason really. But then not too long ago, the call came around from the Oregon Academy of Sciences for nominations for their various awards, and one of them is basically the Oregon Scientist of the Year Award. And it occurred to us that given the fact that Rei is kind of in the process of retiring now, it would be a timely occasion to nominate him and presumably get him the award, because he would presumably eclipse just about any other competition that he might have. So we got that nomination in. He's being given the award. He will receive the award at the Oregon Academy of Sciences annual meeting tomorrow. And so kind of to consecrate that from a departmental perspective, we decided to schedule this seminar now so that those of you, especially all of you new folks that know little or nothing about Rei or what he's done over the years, this is your opportunity to kind of learn about the great old history that goes along with this. It's an interesting mix of people in the audience because most of the people are new. Again, most of you probably will know little, if anything, about the history of the work that Rei's done here over the years. But there's just a handful of people here that are sort of the old guard types that have been here since the way back, and they know all the early history to this. And I just wanted to kind of acknowledge that and point out the fact that in the early days of this department, it was largely an air chemistry, atmospheric chemistry operation, the ESE department. And so there was a whole bunch of work that was done here that later proved to be quite influential in the air realm, and Rei was a big part of a fair portion of that. Now about Rei, I have a little of the standard data here. His bachelor's degree is in geology and botany from UMass, 1958. That was the same year I was born, by the way. His master's degree is from UMass, 1960, and his PhD in botany and plant physiology from Washington University in 1964. And for some years after that, he had a couple positions in industry that were more or less related to plant physiology, ag chemicals, and those kinds of things. And then he wound up at Washington State University, where he got into a faculty track and started doing the kind of work that he ultimately brought here in, I guess I missed that date, 1977. And during that time, he, in large part, teamed up with Aslam Khalil, who's now down at Portland State, and the two of them in various combinations did a whole lot of work that turned out to be tremendously influential on a couple different fronts. One of them, well, I guess I'll let Rei talk about that part of it, so I won't dwell on that. But I wanted to brag for him about the citation statistic thing here. This is also to prove to you that I also know how to use an overhead projector. And so this is a graph of Rei's H-index. And so for those of you that are familiar with an H-index, it's this kind of new in vogue metric for measuring the citation impact of a research scientist. And the idea is it's the number of papers that you've published that have that number of citations. And the idea is that it's supposed to be a more reliable way of assessing people's impact. It's slightly less sensitive to how old or how senior the person is. It's slightly less sensitive to how skewed or non-linear the citation statistics might be. So the way that you would visualize this in this graph here, these are citations for each of his some 200 or so some odd publications. And what we do here is we look up in one of the databases the number of citations for each of those papers, and we sort them in order. So number one is his most highly cited paper, and then it declines down to a handful of them here that have only a couple citations. So I put them in rank order here. I put it in a log scale because it's kind of asymmetric. And then what you do is you go down the curve until this scale equals that scale. So he has an H-index of 34 by these numbers here. So that means 34 papers with at least 34 citations. These numbers, this particular graph comes from data that I took from that Scopus database that we all now have to use as of a few weeks ago because OHSU dropped access to the Web of Science. Scopus database only has citation data back to 1996 or something like that, and a lot of Rei's important work was done a little bit before that. So if you went to the Web of Science, where I got the data when I made his nomination for OAS, his H statistic was, I think, 41. And so the whole reason I'm dragging you through all this is so that I can now make this comparison. If you go back to the original paper for the guy that invented the H-index, he did a bunch of literature searching to try to figure out what big-name scientist typically had by way of H-indexes to give us a sense of what's big and what's small. And he was a physicist, so he was focusing mostly on physics people. And so he looked up the H, determined the H statistic for all of the Nobel Prize winning physicists in the time period that he was doing the paper on. And their H-index was 42. So Rei's was 41, and theirs was 42, which is pretty impressive. With that, I don't think there's anything else I need to say, right? OK. Rei, it's all yours.
Fine, thank you. It has been a while finding a moment that I could get here, and it's not because I didn't want to really meet all you new people or older people that have been here, attributed to, so we say, decadal existence, but still do travel a great deal and got my fingers in too many pies. So I have at least 200 overheads, one for each paper. I'm not going to burden you with 200. But I'm going to restrict my talk today to biogenic hydrocarbons rather than getting into the global mass balances that Aslam Khalil and I worked out on nitrous oxide or methane or carbon monoxide or the chlorofluorocarbons and methyl chloride, a whole host of really very important global atmospheric trace gases versus the more regional impact of these biogenic terpenoid materials. Now, when we started out with this kind of work back about 1959, a year after the member's birth, the only ones that we had any awareness of was alpha-pinene, beta-pinene. Did not know that isoprene existed as a natural plant product. Practically, it was dogma that it didn't. It was in the textbooks of Bonner from Caltech that it just was not a natural plant product. It was part of the Rositka rule of the degradative chemistry of cholesterol, that for which Rositka got the Nobel Prize back in the early 40s from the degradative chemistry. The methacrylate or the methylvinyl ketone or something that came up later in our studies, basically both chromatographically and with the proton transfer mass spectrometer. T-osamine is a very interesting compound because in the summertime here in the Pacific Northwest, when we do get that drought in July and August, invariably your big leaf maples, which are a predominant part of the vegetation here, they pump out T-osamine. It's a very interesting stress compound. It'll dominate the atmosphere. D-limonene you can't get away from, either from plants or from cleaning solutions or from sewer gas. It's just a normal ubiquitous issue in the atmosphere. And then we get down to some other interesting sesquiterpenes. We get into one of the more common ones. And the structure of these sesquiterpenes is exceptionally complex, all the way from no double bonds up to 4 double bonds. And when one looks at the window of the potential 400 out of the 4,000 that we expect that we could measure, they all come out in a chromatographic timeline of not much more than 4 or 5 minutes. So high resolution to pick out some of these compounds is absolutely essential. But copaine is a very, very common one that we'll find here in the atmosphere, and you'd expect it to be much more reactive having an internal double bond than it is, but it exists. The compound of choice that everybody's excited about is beta-caryophyllene. This seems to dominate the emissions from the forest on the east coast of North America, and in all of the work that we were doing down in Borneo and other parts of the, shall we say, these remote areas, we find that beta-caryophyllene and alpha-caryophyllene are very common in the emissions and actually much more difficult to measure in the atmosphere, but they are there. And the reason being is especially the beta-caryophyllene, it just does not survive very long in the presence of ozone. Alpha-farnesene is an interesting compound along with beta-farnesene. Basically, this is one of the building blocks of cholesterol and also a very, very common stress compound, especially in alders and in conifers that are attacked by spruce budworms. You begin to put these compounds out as phytochemicals or sociochemicals that are signaling various parasitic returns to these vegetations, as well as stimulating either parts of the feedback mechanism of these plant volatiles in the interaction with insects. So how did I get involved in this? My first love still seems to be that of geology. And this is an interesting place out in southwest Colorado, in the southeast part of Utah. This is Dead Horse Point, outside of Moab, which now is a great tourist mecca, but I worked there in the summer of 1959. And Moab consisted of one Phillips 66 gas station, a rock shop, and a bar. And 25, 26...
Which one did you use more frequently?
I use very frequently the bar. You'll see some pictures of how young I looked at that time, but I had a job that predominantly was to bring the boys on the drilling rig back to camp after a Saturday night in town. This was a hellhole. This is the top of Dead Horse Point over here. Our drilling rig, this is not for oil, this is for potash. Our drilling rig was basically right down over here somewheres, in this area here. We can look down on it, there's the shelf that I worked on. Unbelievably hot. You couldn't touch any metal without heavy leather gloves. You'd burn your hands. And at that point in my life, after this is my second job in geology, I decided there was something better than dying in this sweltering mess, working for Texas Gulf South, or now International Minerals, as they were digging out the potash. And of course, they solubilize this and bring it up to the surface and then evaporate it and harvest it that way. Our job was to basically just drill and find out the extent of this underground deposit. So a buddy of mine, Dave Briel, had sent me a paper, comments about Fritz Wendt's ideas about the role of naturally produced plant volatiles in the atmosphere. Organic molecules of plant origin is what Professor Wendt called them. I wrote to Professor Wendt, a very well penmanshiped letter, because I didn't write very clearly, and asked if there was any opportunities to work with him, and he said very effusively, yes, there are, but there's no money. But come anyway. And so I did, and these are some of the papers that Professor Wendt had put out in this time frame of the late 50s and early 60s. And of course, the most classic one is basically his paper on blue haze. Now, blue haze has a long history of being described, with all the explorers in the world that describe the Blue Mountains of the Shenandoah Valley, the Blue Mountains of Australia, the Blue Mountains in the southwest Arizona that the conquistadores would name practically every mountain Azul, and the Blue Mountains in Costa Rica, anywhere as you go, to the Purple Mountains in the Dai part of southwest Yunnan in China. Whereas this concept of blue haze, blue mountains, is a very, very ubiquitous feature of geography. And Leonardo da Vinci actually spent quite a bit of time exploring this, and it was his idea that this was really the emanations from plants that were causing this discrete haze of the atmosphere that he used in his famous paintings, the Mona Lisa and the Madonna on the Rock, to give this term called sfumato, which was the multiple layers of haze that he put on the photograph, on his paintings, to give the perception of depth. Besides just the geometric perception, he actually coated his paintings with different grades of lacquer to give this veil, this perception of depth. He wrote a whole treatise on this. But there still wasn't really science, and basically a lot of Professor Wendt's work was basically the work of very astute general observations. Now, one of Professor Wendt's long life friends was Aries Hagen Schmidt. Hagen Schmidt was a chemist. They're both Dutchmen, and they both ended up at Caltech in the late 30s. And during the 40s, Professor went his way on plant physiology, looking at the air-hot greenhouses by which they could clean the air with charcoal beds and the plants could grow without all of the air pollution effects that were quite rampant at that time in the 40s in the Los Angeles basin. Haze was an organic chemist who was really fascinated with odors, and he was trying to understand the composition of the odors of pineapple. And the only way to do that at that time was to basically collect a large volume of sample, freeze it out, and then run it through infrared spectroscopy, or they had no chromatography at that time, no gas chromatography in those days. And he was smelling it with his nose, as all good chemists, we use our nose, and it smelled like smog. And that launched his entire career into understanding what really was the chemistry of smog. And Haze is attributed, he eventually became the senior member of the state of California for the Air Pollution Control Agency, but he is the father of photochemical smog as we understand it versus the London smog, which is a sulfur reductive atmosphere versus an oxidative atmosphere, because nobody could appreciate how you could take auto exhaust and the sulfur emissions that were rampant from the refineries at that time in the Los Angeles basin and convert these to this eye-irritating, high ozone, high oxidant atmosphere. And it came out to be quite simply just hydrocarbons plus the excess of nitric oxide that would oxidize to nitrogen dioxide, and then the photolysis of the nitrogen dioxide to give you atomic oxygen, a host of free radical mechanisms, and you would spin off all these peroxides as well as excess ozone. We always think this was so de novo, and I don't mean to take any credit away from Hagen Schmidt, but the gentleman who did this first was John Tyndall. And we all know the Tyndall effect, and it's unfortunate that that is possibly the most banal of his discoveries. He was a phenomenal genius, and he is the one who did the first photochemistry. And I followed in his footsteps under Professor Wendt's tutelage, where we would take carbon arc lamps that were used at that time and earlier as the light source for projecting movies. And movie theaters rent these, bring them out, put them in position with water filters to knock down the heat, and then we would reproduce John Tyndall's experiments of putting in amyl nitrate, of putting in other organic vapors, or the tinge of vapors off a nitric acid bottle with some geranium leaves or some rose petals, and observe the photolytic effect of what was generated. And invariably we would get exactly what John Tyndall described in 1869 in all of his experiments on the photolysis, the generation of very, very small particles, so small they couldn't reflect light, they could only refract light. They were less than 1/10 of a micron in diameter, and hence we had blue haze. Now, John Tyndall was also a geologist, and very, very famous as the man who, as part of a team effort, finally described how glaciers move. So he was a very, very active person. He climbed many of the mountains in Switzerland, some of them for the first time, but his real love was in exploring electricity and atmospheric physics events. He's also the father of the medical history aspects of the epidemiology of the transmission of diseases in hospitals by way of the particulate material that is in a hospital or the spores of various microorganisms. So a very interesting person to read, his life's history and his work. Well, the one thing that came out of Professor Wendt's work was the magnitude. How much of this material was going into the atmosphere? And it was totally unbelievable that one could have something on the order of 175 million tons of this stuff, this terpenoid material. And no matter how you calculated it, either by way of which Hagen Schmidt did, was looking at the amount of material that was in the sagebrush, or the various mechanisms that Professor Wendt used, or eventually what I did as a graduate student. I told you I was young looking. Those are the younger days. You can imagine this guy trying to boss half a dozen burly guys on an oil rig. You'll understand why I quit the job. But anyhow, that was back in the very early years of 1961 when we got a grant from the National Science Foundation. Our work was so iffy that all they would award was $20,000. And for that $20,000, we got, I'll tell you the price of inflation, enough money to build a very specialized trailer, buy a truck, put a camper on it, put gas chromatographs and everything else in there, but no money for the student. And fortunately, I was able to get a job at Monsanto, get trained and learn my craft on gas chromatography with Les Etry and the boys in the analytical laboratory down in 2nd Street, just about 3 blocks away from Budweiser. And those were very free lunches, very good lunches, and didn't interfere too much with the afternoon's job. But that's what we did. We built the equipment. We took it out into the field. We went around the United States all the way from Georgia and South Carolina and New Hampshire and Virginia. This is El Porvenir Canyon, about 10,000 feet up in the mountains of New Mexico, measuring what was in the air. Measuring it directly. Pretty iffy. We knew that their plant volatiles were coming out of the plants. These are original chromatograms from 1960 with just packed columns, and basically at that time we didn't even call it gas chromatography. The instruments were called vapor fractometers. Vapor fractometers made by Perkin-Elmer, model 154 in England. And you know, today when I analyze air and I look at 100, 200 compounds in it, or look at vegetation emissions, it still is almost always dominated by alpha-pinene and beta-pinene and paracymene, also the eucalyptol, which you'll see in a moment, which is 1,8-cineol. Now these are precious to me, so I put them in some protectors, but I pass them around so you can see what kind of data we were working with, the quality of the data, even back in 1960, 61, 62. Now these are the emissions that come off the vegetation when it is enclosed. These are much higher levels than what you would measure if you were measuring directly what was in the ambient atmosphere. But you could always pick out the alpha-pinene peak and the beta-pinene peak on occasions. And what really surprised us, and I spent quite a bit of time fighting the literature and the gurus who said they knew better, and that was the fact that we could pick up on occasions isoprene. And the predominant place that we picked up isoprene was not in Missouri, but it was down in the oak forest of Virginia and South Carolina, and up through New Jersey and even into southern New Hampshire. That isoprene, this compound that always came out right on top of the air peak, and as soon as you enclosed willow leaves or cottonwoods or liquid amber or sycamore or oak, that's all you got. There was just a gargantuan flush of organic carbon coming out at that retention time on the gas chromatograph. Just to give you an idea that the eucalypt is also a very strong producer of isoprene, and 1,8-cineol, which would be eucalyptol. Right before that, also when you get down to Australia, you pick up quite a bit of paracymene. It's an aromatic compound, not a terpene. Interestingly, it's almost always associated with the terpene photochemistry. Well, all good things come to an end. I got my degree. I have been commissioned in the 7th Cav, and actually in the Army, assigned to the Armor Division at Fort Knox, Kentucky, in 7th Cav, and I had to go back. I now owed Uncle Sam almost 4 years active duty. So in 1964, the summer thereof, after many, many, many hopeless correspondence to get transferred out of Armor and into the Chemical Corps or something else, I eventually ended up getting transferred to the Medical Service Corps, Fort Sam Houston. Spent the next 3.5 years at Walter Reed. And this is a photograph of one of the TDYs. I was in one of those political slots that nobody was supposed to be in, so the commanding general and the colonel could always have a guest come in and visit. I occupied that spot, so anytime they wanted somebody to come, I got shipped somewheres. This is in Panama, and this is a very, very interesting project I can talk about now. At that time, it was classified. And this was trying to figure out from the concept of organic volatiles, what was going on with the degradation of listening devices that we had inserted into the hard wire of the Viet Cong on the Ho Chi Minh Trail. They were failing. They had to be recovered, brought back to the Panama Tropic Test Center, and there take a look and see what was going on. In conjunction with Bob Hutton, who was a microbiologist out of Fort Detrick, we eventually were able to come up with a very plausible explanation and a way of reproducing it. What you have here is nutrient agar that's been inoculated with a wild population of fungi and other microbial organisms from the leaf surfaces and the leaf debris of the jungle of Panama. And here you have the non-nutrient agar now has been inoculated with a water condensate, which is just the atmosphere that we cryocondensed and got a soup of water and whatever organics were in that water. And enough carbon in that condensate to allow microbial growth, a commensurate type of microbial growth. Here's one of the first devices that it's a prototype of a Summa canister. For those of you who know what a Summa canister looks like, it's just a couple of beakers upside down with glass intake pipes, blowers, and this was inserted in either dry ice or liquid nitrogen. The problem we had in Panama was that or any other tropical area, that you would very quickly have too much frost buildup, and that would insulate your system. So we put in a stirrer to break down the frost that was building up on the walls here, and thereby increase the amount of material that we collected. Later, I'll show you a much more advanced, if I have time, aspect of this as to when we finally went with Bobby Stevens and Chuck Lewis at EPA in the mid-90s, where we could actually fractionate cubic meters of air, 2, 3, 4 cubic meters of air, and take everything out of it and fractionate it so precisely that we're getting 70% of the material in one fraction was all oxygenate, and 70, 80, 90% of the material in another fraction was all hydrocarbon. And this was the basis for many of the papers that came out of EPA eventually, showing that the predominant radiocarbon that was in this organic gas, the commish in the atmosphere, is separate from the particulate material, was of biological origin. It was not dead carbon, it was live carbon, carbon-14. So when I got out of the Army, I went to work with Dow Corning, Dow Chemical in Midland, Michigan, to work on organosilicon chemistry. It was a very good, very well-paying job, and I figured I was going to work all the time, but it didn't work out very well for my wife. She didn't like the mosquitoes or the cold weather, and that basically, after a year or two, moved us on. And all the time that I was stationed in Walter Reed, which was a marvelous place to be, every opportunity that I got, I would give a lecture on isoprene and the terpenes and all the measurements we were doing, because I did have gas chromatographs by that time at Walter Reed, and the American Chemical Society and the Air Pollution Control Association were always having some form of an annual meeting in the district area. And so I was reasonably well known by that time amongst various academics, and this is actually a diagram from the very first grant that I got funded by the EPA. And it was to show that we could build a very simple little heat exchanger. This is very simple. There are some over in the laboratory that have 60, 70 tubes, and that we could pull air into this device. We could collect the liquid air here, and then we could take this apart at our leisure back in the laboratory. One of the unique features of the way this was set up were the kind of orifices that we would use. This was all designed to work with batteries, or actually in this case here with no batteries, no electricity. And the issue was, well, you can get any kind of big gulp, but you get a skewed curve with unregulated intake. We were able to develop various critical orifices. Needles at that time were apropos, and we could get a very flat intake for whatever number of hours. This is the integration with an old disc integrator used for integrating the peaks in gas chromatographic peaks. I give an idea of how flat this curve was, so we got truly an integrated sample of the ambient air. And lo and behold, if you work in a Doug fir forest, you get a Doug fir monoterpene fingerprint. Now, please remember, we're working at this time chromatographically with pack columns. We're working with predominantly cryo-transfer procedures of freeze-out loops. We're not working with the use of solid absorbents. We're not working with the ability to go to the extended range of higher molecular weight compounds. We're pretty much focused on what EPA mandated, which was C2 to C11. Here's the very first person that I hired on that grant, a very famous person at Battelle Columbus. This is Mike Holdren, working up in the mountains, Ponderosa Pines here, of the hills and the mountains outside of Moscow, Idaho. And so that began an entire focus on working on biogenic hydrocarbons. And as a result of that, I made a classic mistake. I accepted a nomination and appointment to EPA. You have to remember, EPA was founded at that time, about 1970-71, by President Nixon, amalgamating 64 different government agencies concerned with air pollution, and I became a member of the first Chemistry and Physics Science Advisory Board to EPA. And lo and behold, that I didn't know that this would eliminate me from any EPA funding. So, what do you do if you can't go to them?
Print, right?
What?
You have to read the small print, right?
There wasn't any small print at that time. So, what do? We went off into the tangent at that time in the early 70s of looking at ozone, and I was just ancillary to the work. I worked with a person by the name of Elmer Robinson, a marvelous guy to work with, who with Bob Robbins developed and invented the instrumentation at Stanford Research for the ability to measure carbon monoxide in the atmosphere for the first time quite reliably. We tried to get funding, NSF funding on this, but I think you have to appreciate the tone of the time in the late 60s and the early 70s. We're just at that time getting papers published against this great activation energy hurdle we have to go over, that isoprene really was a natural plant product. And we spent 3 years dotting the I's and crossing the T's, that one, isoprene definitely was produced in roasted coffee, but why wasn't it a dehydration product? Rohith, Dr. Ganawandena has seen that when we're working with other compounds, that you can make isoprene just in the processing of the sample on the front end of the gas chromatograph. And it went on and on and on and on, but finally it became accepted that it was a natural plant product. And about that time, other people, and myself included, we discovered that the primary hydrocarbon coming out of human breath is isoprene. Now, this really triggered a lot of studies to begin to figure out why and how plants produce isoprene and why humans produce isoprene. And of course, eventually this ended up in all of the statin chemistry of Zocor and Lipitor, that if you can block the initial fundamental pre-isoprenoid isopentenyl pyrophosphate biosynthesis step, you can then truncate through this metabolite in your liver the ability to make cholesterol. So this was way, way back. But couldn't work on the hydrocarbons per se, so we ended up working on ozone, and this gives you an idea of what our Cessna 336 looked like out of Pullman, Washington, and these are hydrocarbon levels above and below the mixing layer as related to ozone. I won't get into that in that much detail. I just want to show you that under the carpet, behind the door, I had 3 other guys working for me. The person sitting down at the bench is Eric Grimsrud, who went on to be a professor of chemistry at Montana State over in Bozeman. And recently, with his help, through this air bank, I don't know if I'll have time to talk about, but we actually, for over 10 years, collected, Jim Mohan did, along with Steve Crawford and Dr. Ganawandena, out at Cape Mears, large cylinders 35-liter cylinders were leftover World War II oxygen bottles from the bombers that we cleaned up, and we could fill with air cryogenically, no pumps in many cases, sometimes with pumps, bring these tanks back up to 300 pounds gauge pressure bombs really for all practical purposes, and use this compressed air as the calibrant gas that was then the reason that we were able to go out around the world and measure real-time Freon 11, Freon 12, methylchloroform, carbon tet, because these calibrant gases that we were collecting at the coast were so stable that you could measure the drift in these tanks to plus or minus 1 part per trillion, 1 to the minus 12, and it's unbelievable that the volume of sample that was used was no larger than the volume of a new eraser on the top of a lead pencil. You stop and think of how exquisitely sensitive was Jim Lovelock's electron capture detector. We truly were down there into the realm of measuring next to nothing. And it was so much easier than trying to measure all these dastard hydrocarbons, of which at that time we didn't have mass spectrometers, so we did not really many times know what we had. Well, out of this ozone work, the other chap is Sherry Farwell, went on to be NSF program director and then up to South Dakota, and Hal Westberg stayed on at WSU, retired a few years ago, and is now raising horses down in Tri-City. But that was the team, along with Joe Spadaro, and eventually with Dennis Schutzel at University of Washington in Seattle. We would generate aerosols of blue haze from terpenes and then impact these on a plate, and Dennis would try to do a thermal desorption into a high-resolution mass spectrometer so we could tell potentially what were the fragment patterns that were rearranging to make all this sticky stuff. And it is sticky because every time you in this room use a piece of Scotch tape, the tackifier in that Scotch tape is nothing more than ozone-treated turpentine. They use a special grade of turpentine. It's a gum turpentine rather than a wood turpentine, but that's why it smells so nice and one reason why it's so tacky. Now, out of this ozone work came something that became very controversial and very, very important. And that is looking at what happens to an air mass when it moves from Chicago and then ends up in Newark, New Jersey, or Raleigh, North Carolina, or an air mass originates in Atlanta, Georgia, and ends up fumigating Boston, Massachusetts. The critical aspects were this part of the curve over here, that you have the input to the photochemical, the urban photochemical cycle. You're making more oxidant, and then you've got a decay of this, and this blob, as it was designated by some people, they could actually plot this meteorologically and with other mechanisms, watch this move across the Midwest, across Ohio, across Kentucky, and every time it got a new injection of oxides of nitrogen, boom, up went the ozone level. But also quite interesting was that it was getting a new infusion of reactive hydrocarbons. And this eventually got into a paper with Bill Shamides out of Georgia Tech. He's now gone on to be an administrator in one of these global environmental wildlife, I think, World Bank organizations. But this was what really triggered a real interest in the role of the biological emissions, was the fact that the ozone precursors coming out of Atlanta, Georgia, were responsible for the ozone that was being measured, and they were trying to control in Newark, New Jersey, or in Philadelphia, or in Delaware. And the intervening pathway that was causing, or the addition that was causing the problem, was all of these oak trees that had taken over the Piedmont or the Carolinas, because when we brought in with the U.S. Department of Agriculture the fungus that killed the Native American chestnut tree back in the 1920s, the trees that came back were oaks. The chestnuts did not make isoprene. The oaks made isoprene. Isoprene is exceptionally reactive compound photochemically, and it was adding to this great bubble of ozone. It was making it almost impossible for the controlling agencies to have any kind of a strategy that would regulate or keep ozone down. The original ozone standard at that time, back in the 70s, was just an ambient air quality standard of 80 parts per billion. And above the mixing level at 5,000 feet typically, these are the kind of levels you'd see 60 and 20, medium around 40. The majority of ozone that is in the atmosphere is basically drift coming from the stratosphere, drifting down across the tropopause, down through the troposphere, and again predominantly in the mid-latitudes where North America sits in the 40s, 35, 40, 45, 50. That's the main corridor that you get the return cycle of this downward drift. And so here you see the kind of net that you're allowed to have under a normal median condition. You're only really allowed to make about 40 ppb anthropogenically before you, quotes, exceed the standard. And if you look at the surface component of natural photochemically reactive hydrocarbons like isoprene, you see you really can generate, again, a respectable amount, a nominal amount. We're taking the median values. It doesn't give you much of a window for the air pollution control agencies to roll back the oxide of nitrogen emissions, and this is one of the things that they were complaining about. This became highly politicized, and rightly so. So Elmer and I decided, rather than be traveling all the time back to Washington, D.C., the opportunity arose that we could do something equally as interesting. We could fly Lear jets around the world. And so over a course of 4 or 5 years, I don't know how many hundreds of thousand miles we logged with different students and whatnot, but this was to take a look at the chlorofluorocarbon issue that was emerging in 1973. And why we were positioned to be one of the leading teams to get into this was that when you're working in upper state New York, or you're working in western Pennsylvania, or you're working in some other remote area looking at what is the composition of the natural atmosphere, one thing you'd like to know is how much urban air is coming into your test site. And Freon 11, the trichlorofluoromethane, is just superb. At that time, everybody had underarm deodorants, squirt, 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 squirt. Every urban area was a gargantuan bubble, a wall of Freon 11 that then would get transported and diluted into remote areas. And we could measure this real time, every 15 minutes, gas chromatographically, and we could tell changes in the atmosphere on the order of 1 to 2% in the composition of the Freon 11. A phenomenal tracer. Now it's unequivocal as to how much of the total hydrocarbon burden that we're seeing is anthropogenic, potentially, and how much is natural. But the chlorofluorocarbon issue wanted to know what was the global distribution of Freon 11 and Freon 12. And at that time, all we had was Lovelock's instrument, which was a tritium foil, low temperature, where we could measure essentially 2 very strongly absorbing cross-section capturing species, Freon 11 and carbon tet. And so we put this on a plane with Joe Krasnick and Elmer, myself, and a couple of pilots. We were smart. We leased an aircraft out of Canada so that when we flew into other parts of the world, they thought we were the Coast Guard because we didn't have numbers, we had letters on the aircraft. It was remarkable, some of the adventures we had. And we're also very lucky to come home alive because south of Palma Island, we lost an engine at 40,000 feet. And I never really do like computers because the computer kept telling us we weren't going to make it home. We've got to burn up all our fuel. Jet aircraft, when they lose altitude, the fuel consumption goes up. But we made it back just by the hair of our teeth on that flight. And so that launched a whole career that brought here to Oregon Graduate Center at that time in 1977, where it really went forward with the measurement of the chlorofluorocarbons, of Freon 11s, right up to a few years after the Montreal Protocol We did it until we got kind of bored with doing it. But we had 5 stations around the world working real time. And after a while, within the group, we began to have divisive opinions. This is a graph showing our work from, on this program. We actually started back in '77, but this is for the Ale gauge program, which started in the late '79s, giving you an idea for different stations around the world: Tassie in green, Samoa in pink, Cape Kumakahi over on the coast of Hawaii, Cape Meares out here at Tillamook, and then Barrow, Alaska, where we were. These are actually flash samples, not real time. And this gives the calculations that Aslam made, Aslam Khalil, of the trend. And this is post the Montreal Protocol. So you can see as soon as you shut off the use of Freon 11, you could begin to see the rate change. The point is that we had very, very, very high intensity data, both real time and flask. And eventually I argued that, well, for compounds that have lifetimes of 100 years or 60 years or infinite, why do we have to have all of this ungodly dedication to very expensive equipment, wearing people out? I don't know how many trips Steve Crawford made to Australia, but I would assume that's well over 20 some odd trips, or he'd no sooner get a machine set up and operating correctly in American Samoa, hit Hawaii, and he'd have to go back again because it went down. Whereas you could do this with the flash samples, and this gives you an idea, again, on Freon 11, looking at real-time versus weekly flash samples, and the fact that after we get out of the real-time measurements in blue, we could continue our own work here and show the rollover and the decay. Of course, other compounds that we measured, like methylchloroform, that actually plummeted to the point that you can barely measure it in the atmosphere. Now, you can't measure it directly. You have to go with enrichment procedures. But that's a whole different talk. But out of that came 2 very important things for biogenics. We did a lot of work on how to measure nitrous oxide and methyl chloride. Again, methyl chloride is the only natural source of chlorine. Well, I could go on until 4 o'clock this afternoon, but I think I'll close with just some of the fun things that I'm doing right now. I've set up a small laboratory at home in my spare bedroom, and one of the unanswered questions, a real hard question to answer, I hope this will show up. It doesn't. But that is the question of measuring ozone. Ambient levels of ozone are so critical to know. This particular recording right here has nothing more than a piece of raw copper tubing, about 1 meter length of copper tubing, and the ozone in that device, instead of reading 30, 40 parts per billion or 35 ppb on the upslope, or 60 or 70 on the upslope coming out of Portland, is -1. Just 1 meter length of 1/4-inch copper tubing, raw copper tubing, eats up the ozone. We don't have to go with Ki, we don't have to go with sodium thiosulfate, which are very effective, but they're very hard to control in an Oregon or a Pacific Northwest environment, because humidity will basically cause these things to deliquesce, and then you've got all sorts of junk going on this wet surface. The copper tubing doesn't have the capacity, but then again, I always like to change out things after each experiment. Here, sitting up on the patio at home, give you an idea of 3 instruments being tested. These are the copper. They're bright copper, by the way. They're not this burnt copper. The color inkjet didn't do a very good job of it, but you get an idea of the coil, 1 meter, and going down through, in this case, just 1 Tenex trap or a carboxyn type trap. And we have found that, again, things that we developed with the Suma canisters years ago, these mechanical frequency control, flow control is quite important. And then down here, again, measuring for quality assurance that we're getting the right vacuum, and just some small pumps. These are fascinating little pumps. They're just 12-volt pumps, and they'll pull to 29.7 inches of vacuum. 29.9999 is absolute. Fascinating little piece of equipment. But this is all focused on one thing, and that is being able to measure the sesquiterpenes in the atmosphere. Remember I told you that all the way from no double bonds to 4 double bonds, with beta-caryophyllene being the one that everybody's most interested in and the one that is causing me the most problems. Well, the very first thing that we discovered last year, I gave a paper on this in Brazil, thought that was a good place to go give it, in Manaus, up there on the Amazon River, and that was at that temperature of 30, 32 degrees Celsius, we could report data that at 0 degrees Celsius we had all the sesquiterpenes we wanted in the ambient air outside of Portland, Oregon in January, December. In other words, it's phenomenal. These things are coming out of something. The problem was that the fingerprint of what we were seeing in the air in December and January is not the fingerprint that we see coming off a normal Doug fir. Of course, the big leaf maples have lost their leaves, the alders have lost their leaves, et cetera, et cetera. So the next thing we started to do this fall was to follow up on some interest of what comes off dead leaves. These are big leaf maple leaves with just a couple of these sumacanuses cut in half, and then we put here a speme fiber, a solid, I forget what speme stands for at the moment here. Anyhow, it's a very interesting little device for concentrating the gases. The fiber is exposed down here. It's just about 22, 23 gauge in thickness, and it absorbs either on Tenex or carboxyl material or other materials that you want, divinyl benzene or polydimethylsiloxane substrates, the gases, and then you can inject that directly into the GC. And this is looking at what's coming off of these dead leaves, predominantly sesquiterpenes. So then we have no end of jars. And I move one of the GCs into my wife's spare bedroom, her study. You can still see, well, you can't see it in this picture here, but over here are her famous pictures of sharks. And just the helipackage with the speme, the mass spec here, and then over here another 5890 with a thermal conductivity instrument so that we can measure very carefully in the enclosures the rate of accumulation of CO2, so we know how much respiration is going on. We collect these samples in the springtime, in the summertime, in the wintertime, and here gives you an idea that sample collecting here at roughly 2 meters off the ground, down here right at ground level. This is just a pump with some canisters that I'll explain for in a moment, but the difference between here and here is phenomenal for these sesquiterpenes and for other compounds. This is in an alder group. These are the red alder, Alnus ruba. The canisters were used to collect just whole air samples, because if we grab a whole air sample, we can very, very accurately measure exactly how much toluene, BTEX, benzene, toluene, ethylbenzene, xylenes are in the atmosphere, because they're ubiquitous. Calibrate that. We use the unique feature of toluene that we use mass 93, a very common mass that we have in the monoterpenes and in the sesquiterpenes is mass 93. Dr. Ganawardena worked this out decades ago. Was it decades? 2 decades? That you could take a fraction, a percentage of the molecule of mass 93, calculate that to the entire abundance and relate that to its concentration across different molecular weights, different compounds. And we use that for calibrating and calculating exactly how much of this or that compound is there, as long as we can get toluene. And toluene, I say, is ubiquitous. And I don't care if the toluene is coming from the plants, which in some cases it is, or it's coming from auto exhaust. Once we can quantify one compound with the equivalent mass that we're interested in, we're home and off and going. Now we had our snowstorm of this winter, and sure enough, we're still out there collecting. Not this time, there's too much snow on the top, but now we're collecting quotes with the domes. And to make a long story short, the thing that's most fascinating that has come out in the past couple of weeks actually is that the main source of the sesquiterpene fingerprint that we see in the wintertime versus the fingerprint that we see in the summertime or the spring is coming from the lichens. Now, I've done a lot of work with lichens over the years, and they always sort of produce nothing. And I put a dead leaf in here because even these dead leaves over here are still producing a bit of the sesquiterpenes. But it's predominantly coming from these lichens, not at exceptionally high rates. If you enclose a Doug fir bough, say 5 grams, and you enclose 5 grams of lichen material in a jar, the rate of emission between these will be off by a factor of 100. In other words, the Doug fir is putting out 100 times more than the lichens. But the lichens are doing this. And we're doing this at ambient temperatures of 28 Fahrenheit to about 50 degrees Fahrenheit. So we're making the enclosures under the kind of conditions that they're experiencing. The moss is even less than the lichens. But the lichens and the moss, man, they're respiring. And this is done without direct sunlight, because that's a whole other effect when you add sunlight into the system. And to give you an idea, as we've all seen it along the side of the road, the incrustation of the vegetation with these lichens. Here is a box elder, Sambucus, and you get an idea as to how heavy is the incrustation of the vegetation here in the Pacific Northwest. If you go down Logie Trail, you wonder how some of the branches on the big leaf maples can support such a heavy load of moss. And just in passing here, gee, I left out all the political crap that I got chastised on years ago. This will just give you an idea of a SPEME chromatogram looking at a lichen just yesterday, looked at it again this morning. It's been in the jar for 12.5 hours at roughly 34 degrees Fahrenheit. Here are the sesquiterpenes, about 5 or 6 of them out here. This is solanine or eudesmine. It's actually, the mass spec can't tell the difference. Over here we got cotidine, down here we got copaine. This compound we cannot identify. It's unusual. It's got some chlorine in it. This is a monoterpene. This is 1,4-terpenine. This, interestingly enough, we find it hard to believe, but it's real. It's paracymene, the aromatic correlate that always is associated with eucalyptus type foliage. And this is C4-methyl ester, C5-methyl ester, C6-methyl ester in this area here. And that's the kind of chromatogram that we're seeing, and we can track and go on from there. Well, this interest in biogenic emissions ceases to amaze me. I have the text from the chastisement and the attacks that were made upon President Reagan back in 1980, 88, his comments about killer trees. Now this has got a very interesting history. We got a few more minutes. That based upon what I had written up and published in '72 about how much material was coming out of trees contributing to air pollution, doubled what Wendt had said at 175. I'm about 430. By the way, the last Gordon conference, my number on the monoterpenes emissions is only off by 5%. That's 25 years later. Down here is Bill Schmide's paper on the role of biogenic hydrocarbons in the urban photochemical smog of Atlanta as a case study, where all of this smog is being created from the infusion of new reactive biogenic hydrocarbons along the Piedmont from Atlanta on up to Newark, New Jersey, due to the tremendous overgrowth of the oak trees that have come in there. Well, Reagan was right. And secondly, Reagan never said this. This killer trees is no official statement anywhere in press releases, and I'm not the only one that's done the research. Tom Shockey at University of Wisconsin has spent a lot of time trying to track down who said this about the killer trees. What Reagan had, more than likely, was a briefing that when I was getting into the chlorofluorocarbon issues, I was the group leader at Pullman, Washington, one of my students, Pat Zimmerman, I had him take over an EPA project that I really wasn't supposed to be that deeply involved in, gave him all the equipment, and set him off with Don Stearns and Bob Watkins. Don Stearns worked here. Bob Watkins still here. He's retiring now. Went around the country, and they enclosed vegetation. Unfortunately, they enclosed the vegetation to the point that they so disturbed it, they so heated it, they cooked it, they got these gargantuan emissions, and that was one of the reasons I didn't get in the project. It's wrong. You can't do it that way. You can't enclose it and sweat this stuff out. Well, the numbers came up, and they flabbergasted EPA. Don Sutherland was the project manager. Unbelievable emission rates coming out of the Tupelo forest of the southeast. And that's the kind of information that most likely President Reagan got, was an EPA report prepared by Pat Zimmerman showing this tremendous flux of hydrocarbons. Now, for the wrong scientific reasons, it stimulated a terrific amount of money into the program. But it was Bill Shamides that really identified this recurrent infusion of just the normal emissions causing the smog, which was a carry-on from Joe Buffalini, Basil Dimitriades, and Elmer Robinson's idea of the progressive, back in the earlier 70s, infusion of further emissions creating the recurrent of more ozone. Well, the last slide, now I've lost it, is yesterday's newspaper. I didn't want to talk about methane at detail, or nitrous oxide, or all the other trace gases we've played with, but here we are yesterday on the 26th, and here they are in New Zealand with ungodly automated devices, 10 of these chambers to measure the respiration and the burps of the sheep and the flatus of the sheep, et cetera, as there's a new emphasis on silencing the lambs. The methane research targets sheep in their belching. And it's quite interesting that in 2003, when I was down there with vets, it was all the fire in the newspapers that they were proposing to tax sheep. Tax. Well, you may laugh at that, but one of the real sensitivities that Professor Khalil and I had in the very early years, 1985 through 1992, working in China on the flux of emissions from the rice paddies, was the political sensitivity that the agricultural practices in China with the rice and the anaerobic activity really were a very major part of the global methane budget. It was very politically sensitive, and for many off and on seasons, work went slow, work went fast, samples disappeared, a whole host of things. So the point is, with this quote, excuse the New Zealand agricultural fart tax, another interesting thing is, we all live in this area of carbon footprints and offsets, that if you sequester carbon, you get an offset. You take something out, you put something back out, release something, you're going to have to pay another offset, a tax. Well, Kepler and his group in Germany, and I spent quite a bit of time trying to reproduce his work, was able to demonstrate in his laboratory that he could generate methane aerobically from plant leaves. We've had very difficult time reproducing that work. But in that case, methane is a much more effective greenhouse gas than CO2. I guess you'll have to have another tax, a methane tax on leaves, a leaf tax, a sheep tax, a cow tax, a rice tax. We already got taxes on people, so the protocol is there. So I leave you to the tax future, seeing what you're going to get taxed on next. Thank you.